Hi, everyone, and welcome to this next section in the SNIA track on computational storage. This session will be talking about, accelerating AI with computational storage and innovating IT infrastructure. Can you believe or achieve the hype? Our presenter today is Dr. Tong Zhang. Tong is a co-founder and chief scientist of ScaleFlux, which is responsible for developing key techniques and algorithms for computational storage products. He's also currently a professor at Rensselaer Polytech Institute, and I kind of got my tongue around, I've been having tongue twisters all day long. All right, so his current and past research span over a wide range of areas across storage technologies, and he has published over 150 technical papers at Usenix, IEEE, ACM conferences, and journals, and served as general technical program at several premier conferences. All right. Sorry. Tong, I will turn it over to you.
Sure. Thank you. Thank you very much for the introduction. Yeah, I will share the slides. And great. Yeah, it's really my great honor and a pleasure to have this opportunity to share our view on about the computational storage. So really the slowdown of CMOS technology scaling really drives the industry to start the transition from we call the traditional CPU-only homogeneous computing towards this domain-specific heterogeneous computing, where the certain computation tasks migrate from the host CPU to other computing engines, including this standalone PCIe accelerators and smart network card that offloads network processing from host CPU, and this computational storage drive that offload tasks such as compression and encryption from CPU. So actually, altogether, they kind of complement with CPU to form a truly heterogeneous heterogeneous computing infrastructure. So we all know that abstraction is one of the key design principles underlying the modern computing systems. And also actually the success of today's computing system really go back to leverage the beauty of abstraction. But unfortunately, this heterogeneous computing really actually by nature tends to break from the principle of abstraction. So as a result, it introduced, we call it like a really non-trivial the trade-off between cost and the benefit. So clearly that to make it practically viable or commercially viable, we must have a, we call the justifiable cost versus benefit trade-off. So actually this explains why, in spite of in the academia, on the research paper, we have so many great results published by the academia over the years. But in reality, in the real world, we only see a few successful commercialization of this heterogeneous computing, such as SmartNIC and the video codec, in addition to GPU. Really, the GPU is the most successful example there. So there's really kind of a mismatch between what the academia promised us and what is happening in the reality. So of course, as one part of the story in the heterogeneous computing, computational storage is absolutely not an exception. So regardless of what kind of computations we want to migrate in from the host CPU into the storage drive to form a computational storage, we have to, or we must have, a justifiable cost versus benefit trade-off. So now let's go back to really kind of computational storage. Its basic idea has been started by academia over the past over 20 years, and the very impressive results has been shown on many research papers. However, the large-scale commercialization success of computational storage, to be honest, remains completely missing. So just because, arguably, because all the solutions developed over the past 20 years, failed to establish a justifiable cost versus benefit trade-off. So turns out it makes no sense to really bring that into the real world. So therefore, whether echo the title of this talk, like whether the computational storage will be a hype or will be a real thing, really totally depends on how well we could find computational storage solutions with a justifiable cost versus benefit trade-off. So the data path transparent compression is really kind of no-brainer. It's a perfect low-hanging fruit to commercialize the computational storage. Its basic idea is extremely simple. The compression is done in hardware along the I/O path, transparent to the OS and the user applications. And because compression is completely sealed, hidden inside the storage drive, we do not need to modify the existing software stack. And also, we do not need to change anything on the existing interface across different layers. And clearly, there's no vendor lock-in problem. So really, this table further compares the different options, like when we to implement data compression, like from different aspects such as CPU overhead, scalability, impact on latency, and the easiness of integration. So apparently, the in-storage transparent compression is the most desirable option. So clearly, the computational storage drive with built-in transparent compression can be really seamlessly deployed in existing IT infrastructure without demanding any changes to the existing software stack. So by simply replacing normal solid-state drive with such computational storage drive with built-in transparent compression, users could seamlessly enjoy over 2 times storage cost reduction without consuming any host CPU cycles. So here, the main use cases just include like a relational database, key value store, and the data like data analytics. So beyond the seamless deployment to transparently reduce storage cost and improve system performance, transparent compression enables a very exciting system innovation opportunities. So as illustrated here, that with built-in transparent compression in the drive, in the computational storage drive, the system no longer has to fill each 4 kilobyte block with valid user data. And the system no longer has to utilize all the LBAs on the logical storage space. So as a result, the data management systems could employ sparse data structure without sacrificing the physical storage cost. So intuitively, we could leverage the sparse data structure to gain system cost and performance benefit, so that will further enhance or significantly enhance the benefit of a computational storage drive. So then we can further justify the commercialization. Okay, so then in this context, since we only need to employ the sparse data structure in either application or the operating system, then we do not need to change the existing interface across different layers. And clearly, there's no vendor lock-in. So as long as different vendors, they can deliver the storage drive with built-in transparent compression, they could, in theory, they could be just interchanged. So therefore, we only need to make sure that the cost of modifying the data structure in applications or operating systems can be well justified by the benefit. So then based upon how much we need to modify the application source code, we could categorize the entire design space into 3 stages as shown here. So really then in the remainder of this talk, I will just use 3 very simple examples in those 3 stages to show that there is a very exciting potential of applying sparse data structure enabled by the transparent compression to gain significant performance benefit. So the first case study is PostgreSQL, one of the most widely used relational database. So first, the Postgres use a parameter called fill factor. So we use FF, stands for fill factor, to control the amount of space reserved in each page, in each database page, like 8K byte, for future update. So the value of fill factor directly determines the trade-off between the database performance and the storage cost. For example, if we reduce the fill factor to leave more space for future update in each 8K byte page, then the database performance will improve. But at the same time, the storage cost will accordingly increase because we reserve more space in each in each 8K byte page. So as a result, the Postgres really by default set the fill factor as 100. That means we do not reserve any space in each 8K byte page for future update in order to minimize the storage cost. But interestingly, once Postgres runs on computational storage drive with built-in transparent compression, the storage overhead could caused by reserved space could largely disappear because Postgres initialize the reserved space as all zero, and those all zeros can be easily wiped out by using the transparent compression. So this naturally enables the Postgres more aggressively set the fill factor to increase the data sparsity without sacrificing the physical storage cost. So to illustrate this, as shown here in this cartoon, let the blue and the black dots represent the operating points when using the computational storage drive with built-in transparent compression and the normal solid-state drive. So with the default fill factor of 100, they both have the same performance, and the computational storage drive can reduce the physical storage cost by half through the transparent compression. But once we reduce the fill factor from 100 to 50, then under normal solid-state drive, the storage cost directly double, and the performance improves. It's very clear trade-off between the performance and the storage cost. But under the computational storage drive with the transparent compression, we can expect pretty much the same performance improvement, but at the same time, the storage cost remains almost unchanged. So, so that will make the Postgres much better take advantage of computational storage. So here we can further carry out experiment. For example, as shown here, we use the Sysbench-TPCC benchmarking under 2 different data set size, like 740 gigabyte and 1.4 terabyte. So here the results clearly show that as we reduce the fill factor from 100% to 75%, the TPS performance, like the TPS stands for the transaction per second. So those performance can improve by about 33%. So under normal solid-state drive, the physical storage space will jump from 740 gigabyte to 9 and 12 gigabyte, or from 1.4 terabyte to 1.7 terabyte. So, but in comparison, under computational storage drive with built-in transparent compression, we see the exactly same, like a 33 TPS performance improvement, but at the same time, the physical storage cost only slightly increase. For example, like from 178 gigabyte to 189 gigabyte, or from 342 gigabyte to 365 gigabyte. So this study clearly show that by simply configuring the existing fill factor parameter to make data more sparse without changing any single line of code in Postgre, then Postgre can very nicely take much better advantage of a computational storage drive to further improve the TPS performance without compromising the physical storage cost. Okay, so the second case study is about reducing the B-tree write amplification. So we all know that the B-tree as the most important data structure, the B-tree powers almost all the relational database in the real world. But recently, B-tree faced a pretty strong competition from another data structure. It's called the log structure merge tree, or we call LSM tree, because of this the two widely cited advantages of a log structure merge tree over B-tree. That is, first, it has less storage space usage, and the second, the log structure merge tree has a much smaller write amplification. But once we run the B-tree on the computational storage drive with built-in transparent compression, then the storage space usage advantage of log structure merge tree will just simply largely disappear. And also, if we want to go one step further, by leveraging the sparse data structure, we may significantly reduce the B-tree write amplification through this page modification logging. It's a very simple idea. For example, as shown here, so associated with each 16 kilobyte B-tree page, we assign 1 4K byte storage space for page modification deltas. So it is very simple. It's extremely straightforward, extremely simple idea, but it is not practically feasible if B-tree runs on normal storage drive. But once we modify the B-tree and runs on computational storage drive with built-in transparent compression, we can significantly reduce the B-tree write amplification and then make the advantage of log structure merge tree pretty much go away. Then here, as for the purpose of demonstration, we have implemented such a B tree we call the B- tree, and compared it with RocksDB, is very popular key value store nowadays that use a log structure merge tree. And also we compared with MongoDB that use a normal B tree. So here the result as shown here, that compared with the log structure merge tree, the normal B tree as shown from the MongoDB indeed suffers very badly from the write amplification, at least 4 or 5 times higher write amplification. But with the modified B tree or B- tree, we can dramatically reduce its write amplification by leveraging the computational storage drive, and even make it smaller than that of the log structure merge tree. So therefore, once we appropriately modify the B tree by leveraging the computational storage drive, then both advantages of log structure merge tree will be gone. So as a result, compared with the B tree, log structure merge tree will become much less appealing in practice. So then the whole industry has to rethink what is the trade-off, like what is the compare, why we want to use a log structure merge tree to replace B tree. Because right now, using computational storage drive with the B tree, then B tree is almost pretty much the perfect data structure. There's no need, actually there's no need to use any other especially for log structure merge tree to replace B tree. Okay, so the last case study is about the design of a hash-based key value store. So like in current practice, when we want to implement a hash-based key value store, we first hash the key space onto an in-memory hash table, And the in-memory hash table further points to the location of all the key value pairs that are packed tightly on the logical storage space, which are further transparently compressed and stored. So such an indirect addressing through the intermediate hash table can maximize the logical storage space utilization. But at the same time, the memory footprint of the hash table is a very big problem. So actually, the high memory cost of the hash-based key value store is really the main reason, at least one of the main reasons why its real-world deployment really pales in comparison with key value stores built upon other more memory-efficient data structures like B-tree and like B-tree and the log structure merge tree. So then, so the leveraging the computational storage drive, we can just use, again, the very simple idea is we call the table-less hash-based key value store. Here, we directly hash the key space onto the logical storage space without going through in-memory hash table. So then, by avoiding the use of hash table, we completely eliminate the memory cost on implementing the hash-based key value store. And moreover, by relieving the CPU from managing and searching the hash table, and then it consumes less CPU cycles. But because we do not use this indirect addressing, then the logical storage space utilization is relatively poor. That means like almost all the pages have noticeable amount of empty space that left unoccupied. So, but once we can fill those unoccupied space with a highly compressible, like a dummy data, like all zero, then we can achieve pretty much the same physical storage cost as the current practice. So in summary, like by using a sparse data structure enabled by computational storage drive, then we can use we call the table-less hash-based key value store to completely eliminate the in-memory hash table without sacrificing the physical storage cost. So by eliminating the in-memory hash table, so this key value store natively has very small memory footprint. And meanwhile, it's a simple data structure directly leads to a high operational parallelism, short data access path, and a very simple implementation. And also, it is not subject to a frequent background garbage collection or compaction or operations. So all these features really enable such a table-less hash-based key value store achieve very high performance at low memory and CPU cost. So accordingly, we implement a key value store that is called a CalXDB, and compared it with two other key value stores, again including the very popular like RocksDB that is built upon log structure merge tree, and the WireTiger that is from like a MongoDB. Actually, the WireTiger is the default B-tree based storage engine for MongoDB. So here, the figures here show that the measured result of average throughput, average read latency, 99 percentile read latency, and the CPU efficiency in terms of CPU cycles per operation. So we can see that the CalXDB consistently achieve much higher performance and at lower latency across all the YCSB workload. And meanwhile, the CalXDB has a much better CPU efficiency than RocksDB and the WireTiger. So the significant advantage of CalXDB, there really is no secret. There's no based upon very simple idea. It really just comes from the sparse data structure that is fundamentally enabled by the underlying computational storage drive. There's no other secret source. Okay, so in conclusion, that we believe, I go back to the question we raised like in the title of this talk, like we believe computational storage is not a hype. It is really a big thing. And indeed, we'll have a real potential to innovate IT infrastructure. And the best starting point is in storage transparent compression. So in spite of this very simple concept, it enables a wide spectrum of data management system innovations. And we have shown 3 case studies of the spectrum. And beyond the performance benefits, the transparent compression has 2 additional huge benefits to end customers. That is, avoid modifying the interface across different layers in the existing software stack, and avoid computational storage drive vendor lock-in. So, so we strongly believe the promise, the potential value of this computational storage drive. We sincerely look forward to working with the whole industry and the research community to really further explore this the whole future potential. So yeah, this ends my talk. Thank you very much.
Thank you, Tom. That was incredibly informative and a great amount of detail. Oh, and see, I see little hands clapping going up the screen. So with that, we will wrap up this session. I'll just remind folks, if you do have questions on the computational storage topic in general, there is a dedicated Q&A session a little bit later today. Thank you very much.
Yeah, thank you.